Welcome to this explainer. Okay, so today we are completely freezing time. We're going to break down one of the most famous, yet honestly least understood events in all of science, the quantum leap. Now, I know we use that phrase all the time in everyday conversation to talk about some massive, sudden change, right? But the actual reality at the microscopic level, it is way more precise than that.
So, let me ask you this. Have you ever actually seen a quantum leap? Well, probably not, because these events happen at a scale and a speed that completely defy human perception. We really only know they happen because of the macroscopic effects they leave behind. But today, we're zooming all the way in. We are going to look at the exact anatomy of a single split-second event to see exactly how an atom absorbs light.
Okay, let's dive right into this. First up, let's meet the atomic stage.
What we have here is our strict roadmap for today. The anatomy of a quantum leap. And what you're looking at here, it is absolutely not chaos. It's actually this incredibly intricate, perfectly balanced, and highly ordered environment. Every single particle has its specific place, basically just waiting for the exact right moment to act.
So, let's quickly define the rules of this microscopic world. Right at the center, you've got this heavy, dense nucleus packed with protons and neutrons. And radiating outward from that are the energy shells. You'll see them labeled here as n equals 1, 2, 3, and 4. Now, the best way to think about these shells is that they act exactly like the rigid rungs on a ladder.
All right, time to introduce the main character of our story, the electron. Right now, it's just sitting quietly on that very bottom rung of the ladder. This is what we call the ground state, or n equals 1. Down here, everything is calm. The electron is stable, and it's basically as close to the pole of that nucleus as it can possibly get. Honestly, it's perfectly content to just hang out right here forever, unless of course something forces it to move.
Which brings us to our next section, the incoming photon. And here is our inciting incident. Entering from the left as this bright glowing wave, we have an incoming photon. This is basically a pure packet of energy, a tiny little messenger of light. And it's zooming directly toward our quiet electron on that n equals 1 shell. The stage is totally set for a collision. Now, what's really fascinating here is the specific formula attached to this photon. Delta E equals h nu. Now, don't let the math scare you. Just think of this formula like a barcode. It defines the exact, specific amount of energy this particular photon happens to be carrying. And in the atomic world, that exact amount of energy acts as the ultimate cosmic key that you need to unlock the next level. Because this isn't just a suggestion, it's a strict quantum rule. Remember our ladder analogy from earlier? Just like you can't, magically float in the air between two rungs of a real ladder, an electron simply cannot exist in the dark, empty space between these energy shells. For our electron to move at all, the photon's energy, that delta E, has to perfectly, and I mean perfectly, match the gap between the shells. If it's even a little bit off, the photon just goes right through like nothing happened. But if it matches perfectly, well, that brings us right to the crucial question. What exactly happens at that exact millisecond of collision when the key actually fits the lock?
Let's dive right into the climax of our story, the quantum leap itself.
We are literally looking at a freeze frame of the exact millisecond that incoming photon strikes our ground state electron. And at this moment, something incredible happens. Pure absorption. The photon doesn't just, bump into the electron and bounce off. It completely transfers its very existence, its entire energy payload, directly into the atom. So let's break down this action sequence step by step, because it's pretty wild. Step 1, the photon hits that ground state electron. Step 2, because that delta E barcode perfectly matched the gap, all of that energy is entirely absorbed. And step 3, suddenly energized and completely unable to stay on that lowest rung anymore, the electron instantly jumps outward. In this specific scenario, it completely bypasses shell number 2 and makes a massive leap straight to the third energy shell. This perfectly captures the crazy dynamic nature of the leap. You can see this literal glowing trail showing the electron leaving the inner shell and arriving at the n equals 3 rung. And here's the thing, this transition happens basically instantaneously. The electron doesn't smoothly glide through the empty space in between. One moment it's at n equals 1, and the very next it's at n equals 3. It hasn't just moved, it has leapt. Now that the leap has actually happened, let's look at the aftermath in our final section, the excited state.
So the crucial takeaway here is this drastic contrast we're left with. Our electron has completely transformed its whole reality. It went from this calm, low-energy, super stable existence anchored down at n=1 to a highly energetic, vibrating state positioned way out at n=3. It is literally like comparing someone fast asleep in their bed to someone sprinting at full speed on a track.
Now, what's super interesting about this new outer shell, this excited state, is that it mathematically represents the exact sum of the original ground state, plus that specific incoming photon's energy. Basically, the electron is now carrying the phantom of that photon around inside it. It's absolutely buzzing with this borrowed power, orbiting at a much, much greater distance from the nucleus.
But, as we know, nature absolutely loves balance. You just can't keep borrowed power forever, right? Since this excited state out at n=3 is strictly temporary, well, what goes up must eventually come down. As we wrap up this explainer, I'm going to leave you with this final, kind of mind-blowing thought. When that electron inevitably loses its grip and falls back down that ladder to the ground state, it has to release all that borrowed energy. It shoots it back out as a brand new photon of light. And that microscopic flash, when you multiply it by trillions and trillions of atoms, it is the exact reason neon signs glow. Lasers can cut through solid metal, and the stars shine in the night sky. So next time you look up at the stars, just remember, you're watching trillions of tiny leaps. Thanks for exploring the invisible world with me today.